Start recording. Okay, there we go. All right.
Sodium loses an electron, it becomes Na+,
and then
results
we
in
get
a
this
crystalline
crystal
structure
lattice,
where we
right, where it's alternating positive, negative, positive, negative, positive, negative, and it doesn't all fly apart because the positives stick to the negatives. Okay, carrying on. La, 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 la. Oh, here is a metallic crystal. It looks kind of like an ionic crystal, but what's different about it? They are all cations, cations everywhere. So this begs the question then, what does positive do to positive? Repels. Why are these guys not flying apart? Yes? Well, let's go and take a little look and see what happens. Here is what's happening at the subatomic level.
us how the positively charged cations in the metallic crystal can stay together. So as an example, we'll take a look at aluminum. Looking at the subatomic structure, we can see each aluminum atom has 13 protons, but only 10 electrons.
Okay, so do you see the 13 protons in the middle? And how many electrons do we have around the outside? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Where have the other 3 gone? They have gone. Do you see them here and here and here and here and here and here and here? They have gone everywhere. Okay? So those valence electrons, they are no longer stuck to their home atom. They're not stuck to a single aluminum atom. They are moving in between one and the other. So
it has given up the 3 valence electrons to what is called the electron C. This is why it's called the electron C model. The space in between each atom is filled by the valence electrons that have been given up by each atom.
We're just going to go back because I
the
want
electron C. This is why it's called the electron C model.
Okay, so when they say electron C, that's SEA, like an ocean. It's like an ocean of electrons with these cations floating in it. Yes? And what do negatives, this little circular blobby region, it's not circular, worm-shaped blobby region is all negative. And then we have the cations, which are positive. What does positive do to negative? It attracts. So although the cations would like to repel each other, those negative valence electrons floating around in between act like glue to stick the positive cations together and keep them from repelling one another too much.
The space in between each atom is filled by the valence electrons that have been given up by each metal atom. So the metal atoms become cations, positively charged ions, and the valence electrons are loose in the spaces between the cations. So what's holding the crystal together is the electrostatic attraction between the positively charged cations and these free-floating negatively charged electrons. And so the valence electrons are not localized to any one particle. They are free to move and occupy the space between the positive ions.
No, you don't. He keeps his sentence going past when he starts. Okay. The word localized. Localized means stuck in one location. Yes? Localized, stuck in one location. So the valence electrons are not localized. Shell 1 electrons are localized. Shell 2 electrons are localized. What about shell 3 for aluminum? They are what we call delocalized. They are free to move from one atom to another, from the space here to the space there. They can do whatever they want to. They can just move around in the space between the positive ions.
They are free to move and occupy the space between the positive ions.
As you can see in this simulation, the electrons move very quickly, and what you are seeing would actually be considered extreme slow motion.
Okay, so are you watching the movement of those electrons? They're just going crazy. They're going everywhere.
So the electrons create a negatively charged space between the positive ions.
And so similar to the electrostatic attraction that holds the ionic crystal together, we have this attraction of opposite charges that are holding the metallic crystal together.
Okay, so we've got these positive ions, and then we have the negative delocalized valence electrons. What does delocalized mean again? Delocalized. Localized means stuck in one place, so delocalized means not stuck in one place. They are free to move. Those are our cations. Those are our moving delocalized valence
So
electrons.
aluminum giving up 3 electrons means that all the cations have a 3+ charge, and each aluminum atom has contributed 3 electrons to the sea of electrons. This creates quite a strong attraction, and we can use this model as a way to explain various properties. For example, there is malleability, the ability to put pressure on a piece of metal and not have it break. So we can pound metal with a hammer, we can pound it into a shape and not have it break. How can this model explain that phenomenon? Well, let's hit it with a hammer and see what happens. Ooh, one last blow. Okay. So
what do you notice? We have deformed the structure here. Yes.
The electrons are like still things together.
Yeah, the electrons, because they are mobile, they can just move along with the moving cations down to a lower place, and they're still in between, so they still stick the cations together. Okay?
as you can see, the atoms were shifting. They didn't break apart. Hitting the metal with a hammer does not break it. Why would that be the case? Well, the delocalized electrons are always there. So any shifting positive ions are going to be able to be held together by their attraction to the constant presence of those valence electrons, that sea of electrons that the atoms are attracted to. And malleability, of course, is also intimately related to ductility. You can force the metal into the shape of wires. So this is malleability. And a nice contrast would be to look and see, why does hitting an ionic crystal not result in this sort of malleability? When we hit an ionic crystal, it shatters. Let's hit this ionic crystal with a hammer and see what happens.
I want you to take a look at that crystal and tell your neighbor why you think it shatters.
Shatters that's the charges for like. Well, I'm not wrong. That's how it works.
And if you don't have any idea, I want you to look right along this plane right here. Look right here. If we look right here, what do we have beside each other? Positive and positive. What do we have beside each other? Negative and negative. Positive and positive. Negative and negative. Oh my gosh, all the way down we have like charges paired up right beside each other. What are they going to do to one another? They're going to repel, and watch what happens.
So no matter how you hit it, you're always going to come to some point where like charges are lined up. And so if like charges are lined up, the result is going to be a great deal of repulsion, and that's going to split the crystal.
Off it goes.
And when ionic crystals cleave, they often leave a very sheer, smooth face if you do it carefully because of the way the opposite charges line up. All right, back to metallic crystals. So why would this very strong attraction result in other properties? How about their strength and high melting point? Well, the atoms want to stay together. They're very attracted to the sea of electrons. And so therefore, the higher the amount of valence electrons given to the sea of electrons, the tougher the metal, the harder it is, and the higher the melting point. Transition metals in particular, like titanium and molybdenum, each of which contribute a large amount of valence electrons.
Okay, so what he's talking about here is that when we have some of the transition metals, they have many, many valence electrons. Like molybdenum has 6 valence electrons. And if you recall, the bigger the charge, the bigger the force. The bigger the charge, the bigger the attraction. So if you have a 6+ ion attracted to 6 electrons, that's going to be a bigger charge than in aluminum, where we have a 3+ charge attracted to the 3 electrons. So when you start to get like molybdenum, it will be a very strong metal, and it will require a lot of temperature to melt it because you have to break stronger and stronger bonds.
To the sea, they are very tough metals, very strong, very high melting points. How about electric current? Can this model explain that? Well, electric current is simply the movement of charge, and electrons are constantly moving through these spaces between the cations. They therefore are very able to carry an electric current.
Okay, so what's going to be happening here is the electrons are currently, they are at present moving this way, okay, from right to left. So maybe we put a negative charge here. What does negative do to negative? Repel. So it's going to be pushing the electrons here, and we'll put a positive charge over here. So what does positive do to negative? It'll be attracting. So we got negative charge pushing and a positive charge pulling, and those electrons, which left to their own devices would just randomly wander around, they are now moving in one direction because they're being pushed and pulled in that direction. And let's see.
In the previous simulation, electrons were moving in all directions. That is still the case, but an electric current occurs when there is a net direction of charge flow. This simulation is simplified in that it is only showing that net direction of electron flow.
And what about the shininess, the luster?
Okay, we're going to pause there because we don't have a lot of time to spend on electricity, and I don't want to talk about the shininess of metals. I want to get to the electricity part. So let's just do a little bit. This is on page 6, I believe, page 6. Okay, so metallic bonding. Metallic bonding is the electrostatic attraction. If you don't remember what electrostatic attraction is, that is the attraction between positive and negative. Okay, and in this case, the positive things are the metal cations, and the negative things are those mobile valence electrons. Ooh, there's another good word. Do you guys know what the word mobile means? Mobile. It means moving. So your mobile phone is called a mobile phone because it can move with you, as opposed to a landline, which is stuck in place. Yes? So they are moving, they are mobile. Okay, and then there's a bit of blah, blah, blah stuff here. So we're just going to blah, blah, blah our way through that. But what we have here is we have a sodium atom. It has 11 protons. It has 11 electrons. So what is its overall charge? 0. This is a sodium atom. Now, if we put a whole bunch of sodium atoms together, they look like this. What charge are those little balls in there? They are all positive. So this is the metal nucleus plus the core electrons. The core electrons are the ones that are not the valence electrons. And when you have a metal nucleus plus the core electrons, that is a cation. But that's not all there is to it. I actually have made a little model here. I'll pass it around in a little bit of metallic bonding here. So we have in this little container styrofoam balls, which represent the, what do the styrofoam balls represent?
Cation.
The cations, okay? But there's something else in here. I have put some corn syrup in here. In fact, I think it was probably almost 15 years ago when I put this corn syrup in there. So this could be quite horrifying, except for that it's so concentrated in sugar, it doesn't go bad. Okay, actually, if you have a high enough concentration of sugar, it prevents the growth of bacteria or fungus, like mold. So this is perfectly good. We're never going to open it though. So when I pass it around, if you open it, you will have screwed it up for us all and you will be here after school cleaning up the mess. Because styrofoam is much less dense than corn syrup. What would happen to all these styrofoam balls if I opened this up? And not just that they're coming out, but they're bringing all those sticky corn syrup with them, okay? So we're definitely not opening this up unless we plan on, hanging out after school with Ms. Spence for an hour cleaning whatever mess is here and making a new one. That sounds like so much fun, doesn't it? Let's avoid that. Anywho, styrofoam balls, will they stick together on their own? No, but if you put something sticky in between them, will they stick together? Yes. What does the corn syrup represent? It represents those valence electrons. And there's actually a little bit of air in here. If you tilt it, the air bubble will move, the corn syrup will move. So it'll move downward according to the force of gravity. Okay, so those represent those mobile valence electrons. I'm going to pass this around so you can take a little look at it if you want to. You can turn it upside down, see if you can get the corn syrup to move down and the bubble to move up. Just don't forget whatever you do. And while we're passing that around, we had one little model. Here's another little model. This one is two-dimensional. Here we have what is that thing? That's a cation. What is that thing? That's a valence electron. And what is that valence electron doing? It's moving around. Look, this one's going this way. That one's going that way. They're all moving in different directions, okay? And because they are moving, what's the word that we use to describe them? We call them mobile, because mobile means moving. And because they are all around in between, we call them a sea of electrons. Okie dokie. Oh, I forgot. We have one more word here. Do you remember what delocalized means? Not stuck in one location. Essentially mobile. Yeah. They are delocalized because they are mobile. Yes. Okay. Okay. We're going to skip this part because it is enriched. So if you want to take a look at that, you can, but we're going to skip it for now. Basically, it just says that metals don't hang on to their electrons very well. It's their electronegativity. Just like when you give a non-metal and a metal an electron, it'll go to the non-metal and it won't stay with the metal. Okay? But if you got a bunch of nonmetals, none of them pull on it particularly well, so they just kind of float around in between. So here is our cation. Here is our mobile, delocalized, valence electron. And of course, these guys can move wherever they want to. This guy can go over here. That guy can go up here. This one can move around whichever direction it wants to, because right now they're just randomly moving. But while they are randomly moving, they are also performing a very important function. These cations are positive. What charge are the electrons? The electrons are negative. So those electrons are pulling on the positive cations. Okay, and the positive cations are pulling on the electrons. So these right here are the electrostatic interactions. I've only shown a few, but you could literally draw more. You could say, oh, here's an electron. Let's draw an electrostatic attraction over here. Let's draw an electrostatic attraction here. Are we okay? Okay. So this is just really, really up close. Here we have our cation. Those are our cations. These are our valence electrons. And what we have is we have an attractive force between them. Why does my pen always make that weird little thing anyway? It is an attractive electrostatic force. Is good? Okay.
massive expense. So then the cations are like attracted to the electrons, but they don't like take the electrons.
No, they don't take the electron. They just, I mean, sometimes they will. Sometimes that electron will slot in to the valence shell, but then because it's not held very strongly comparatively, it will just as easily move to the valence shell of another nearby atom. Okay. Here's another analogy. If you don't like the C analogy, you can think of them as a swarm of electrons zooming all about. Okay? We're going to skip this part because we're mainly concerned about the electricity, but you can see why it's malleable. And here is an example of ductility. Yes. Yeah. If you force copper through a metal die, which basically is like a funnel, it's like a really, really strong funnel. If you don't want it, you can give it back to me. Yeah. I got it. Okay, cool. If you push this wire, this copper down, it gets compressed into a wire. And you can imagine we have these delocalized electrons allowing it to still stick together. Okay, and we're going to skip. They're shiny, also because of the delocalized electrons. Here on page 11, this we are going to take a look at. This end of the wire is hotter. This end of the wire is colder. It is just a law of nature that when you have a hot area and a cold area, the heat will transfer from the hot area to the colder area. And these guys are good conductors because these electrons over here, they move faster because of the heat. They move faster because of the heat. But because they are mobile, they can bash into other electrons. And if something's moving fast and it bashes into something else, it will also speed up the next particle. Okay? And if it gets sped up, that means that the temperature increases. And so on, and so on, and so on, and so on, until all the particles are moving faster, which means the temperature is increasing. If you didn't have particles that could move like that, it would be much slower to transfer the heat. You can imagine if you only have little particles that jiggle, they're going to have a harder time carrying that motion forward and bumping into each other enough to make a difference. Okay? And now the one that is really relevant to this unit, this is good electrical conductivity. Are you familiar with this little symbol down here? The one that goes like this. That is a battery. And the long line represents the positive terminal of the battery. The small line represents the negative terminal of the battery. often when we're drawing circuits, we'll simplify things. We're not going to draw like we're not going to draw a 3-dimensional drawing of a wire, you know, showing all the shading, making it curved and all that stuff. What we do is instead, we usually square off the corners and make a nice rectangle that represents our wire. Okay, so that's our wire. And we've attached one end of the wire to the negative terminal. Now, if you can imagine, in this wire, we have little negative electrons. What does negative do to negative? They repel. So which way are we forcing the electrons to go? They're moving away from the negative terminal. Okay, and they'll go around the corner. And then we can see what's actually happening. We zoom in, further and further and further until we can see the actual little electrons. And you can see they're being pushed to the right. Okay, off they go. And every time one bumps into another, it pushes it along, okay? And then not only is the negative terminal repelling, but we also over on this side have a positive terminal of the battery. What does that positive terminal of the battery do to the negative electrons in the wire? That attracts. So the negative terminal pushes the electrons and the positive terminal pulls the electrons. Yes?
Why doesn't the electrons just stay at the positive side?
At the positive side, because they're also attracted. Because in the battery itself, there's a chemical reaction, and we've sort of isolated half of the reaction over here and half of the reaction over here, and the chemical reaction involves the transfer of electrons from here to here. So the battery itself is moving electrons from the positive terminal to the negative terminal through the process of the chemical reaction. And then we have a net positive charge here, a net negative charge here, and then the electrons in the wire just flow. Once the chemical reaction is done, like once you run out of reactants, that's when your battery is dead. Yeah. Yeah, the battery has, it's actually kind of a paste, but it does allow for the movement of electrons. Yeah, they can be kind of gross. Okay, we're going to watch this video now. All right, we're going to go here. And we're going to say, oh, YouTube. Where's YouTube? Copper ion.
Whoa. R plus, we're gonna do financial literacy.
What am I looking for? Oh my God, have you seen this guy who sits with dogs? It's really sweet. There's dogs that have gone into the shelter and they're like, you know, they've been neglected or abused, and he sits with them and just feeds them little treats until they start to feel comfortable with him so that they can become socialized again. Oh my God, it's heartbreaking, but just really, really sweet. Anyway, I need to find out what page we are on because I need to know what I'm looking at. Okay. Where is it? Okay. What is a copper atom? Yes!
The copper atom has 29 positively charged protons and an equal number of electrons in various shells orbiting its nucleus. After filling the first shell with 2 electrons, the second with 8, the third shell with its maximum 18 electrons, the outermost shell of copper is occupied by a single electron. The lone electron is loosely held in its valence orbit and thus can become a free electron. The ability of
Do you see how that electron is mobile and delocalized? Yes?
this electron to freely move away from its nucleus gives the copper atom its current carrying capacity. Let's take a more detailed look at how these free electrons flow when a voltage is applied across a copper wire. Taking a simplified version of a copper atom with its single valence electron, let's distribute copper atoms along the length of a copper wire. In the absence of a voltage, the free electrons in a copper wire will drift in random directions from the orbit of one atom to another. When a voltage is introduced to the copper wire, the electrons can be directed through the wire with the electrons moving towards the positive end of the source voltage. This movement or flow of electrons in one direction is called electron current flow or just current. Materials that have free electrons and allow electrical current to flow easily are called conductors. Conductors, such as copper, have low resistance to electrical current flow and thus are used extensively in electrical circuits.
Okay. So I thought for the rest of class, if you would like, you can, if you feel like you've studied enough for your test, you can work on pages 11 and 12, or sorry, 12 and 13. Is it 12 and 13? 12 and 13 in the electricity workbook, but you can also study for the test and you can finish any quizzes. When is your test? Wednesday. And just wanted to remind you that the first page of this big thing is all about writing the formulas. So if you practice this, you'll be ready for half the test. But the other half the test is the pages 3 and 4, the second sheet. So first sheet, writing formulas. Second sheet, writing names. Formulas, names. Formulas, names. If you only do one, you'll only be ready for how much of the test? Half of it. So make sure that you're studying both of these. Yes, question.
So does the enriched one have the exact same questions?
It has the exact same questions, but with some hydrates and acids sprinkled in.
So they're not different questions.
No. This has nothing different. You just have more. Yeah. Okie dokie. There we go.